Hey everyone, welcome to today's Explainer. We are going to dive right into what is basically a high-stakes physics mystery. What actually happens when the sky lies to a pilot? We look up and just see this big, empty blue canvas, right? But the reality is, it's this incredibly complex, constantly shifting ocean of pressure, temperature, and moisture. And honestly, if you don't know how to read the invisible rules of that ocean, flying through it can get dangerous fast.
So, here is our flight plan for today. We'll kick things off with Section 1, the altimeter is lying. Then we'll hit decoding QNH and QFE, high to low, careful go, the cold air trap, density altitude explained, and finally, the hidden power of humidity. Let's jump right in.
All right, Section 1, the altimeter is lying.
Picture this for a second. You are flying through incredibly thick clouds. You are completely blind to the outside world, and you are relying entirely on a little dial on your dashboard to tell you exactly how far away the solid, unforgiving ground is. Now, imagine that dial is secretly being tricked by the very air you're flying through. It's a pretty terrifying scenario, but it's a fundamental, everyday reality of aviation meteorology.
But okay, before we can catch this altimeter in a lie, we have to understand what it's actually doing. Because it doesn't shoot a laser down to measure your physical distance to the Earth. No way. Instead, it acts like a highly sensitive barometer. It's just measuring atmospheric pressure. Since air pressure predictably drops the higher you climb, the instrument translates that pressure drop into an altitude reading. But to do that accurately, we have to calibrate it using baseline reference points, which in the aviation world we call datums.
Moving on to Section 2, decoding QNH and QFE. Let's look at how we actually set those datums.
So Aviation solves this calibration problem using what is basically an alphabet soup of pressure settings. Let's decode it. First up, QFE. When you dial this in, it references local station pressure. It essentially ties you to the literal dirt. If you're sitting on the runway and dial in QFE, your altimeter reads precisely 0. Then there's QNH. This one references mean sea level. So with QNH set, your dial shows your altitude above sea level, meaning if you're on that same runway, it reads the airfield's actual geographic elevation. And finally, once you climb high enough, everyone just switches over to a standard pressure setting of 1013.25 hectopascals. This creates these uniform mathematical flight levels way up in the sky. It puts all the planes on the exact same imaginary baseline, so, they don't accidentally bump into each other up in the clouds.
Next up, Section 3, high to low, careful go. Let's see what happens when those pressure systems start shifting around.
High to low, careful go. If you've spent any time around pilots, you've probably heard this. It's basically a secret pilot handshake and an absolute survival mantra all rolled into one. Here's why it's absolutely crucial. If you fly from an area of high atmospheric pressure into an area of low pressure and you don't manually update your altimeter, the instrument naturally senses the drop in surrounding pressure. It feels that drop and wrongly assumes, hey, we must have climbed. To compensate for that phantom climb, a pilot might instinctively lower the nose of the plane. Your altimeter is overreading, which puts you dangerously closer to the ground than you think you are.
So how bad can it actually get? Well, check out this magic number, 27. For every single hectopascal of pressure difference you failed to correct for, your altimeter lies to you by a staggering 27 feet. So think about that. If you fly into a weather system that's just 10 hectopascals lower than where you started, you are secretly 270 feet lower than your dial claims. In low visibility, or when you're flying in the mountains, that's literally the difference between safely clearing a ridge and hitting it.
All right, Section 4, the cold air trap. Let's add temperature to the mix and see how things get even crazier.
Okay, here is the temperature trap. Altimeters are perfectly calibrated for a standard atmosphere, which is 15 degrees Celsius at sea level. But basic physics tells us that air expands when it's hot and compresses when it's cold, right? So in hot weather, the air column physically expands, pushing the pressure levels higher. Your altimeter underreads. That actually gives you a hidden safety buffer. You're physically higher up than the dial says. But in freezing conditions, the air compresses. Those pressure levels pack down densely toward the Earth, so the altimeter overreads. Once again, you are shockingly lower than you think.
Let's actually run the numbers on this, because it is legitimately terrifying. Say you're cruising at flight level 150, which implies 15,000 feet, right over a 14,000-foot mountain peak, but it's bitter cold out there, negative 25 degrees Celsius. You glance at your dial and think, cool, I've got a comfortable 1,000 feet of clearance. Actually, scratch that. First, you have to correct for the low local pressure, say 993 hectopascals, which instantly strips away 540 feet of your assumed altitude. Ouch. Then you calculate the error for that freezing compressed air. That robs you of another 519 feet. So, as you can see here, if you blindly trust your dial without calculating true altitude, you aren't at 15,000 feet. Your real altitude is only 13,941 feet. You are going to crash 59 feet below the summit. The sky literally lied you right into the side of a mountain.
Section 5, Density Altitude Explained. Let's step away from mountains for a second and talk about how the airplane itself feels the air. This brings us to a super important concept, density altitude. So true altitude is where you actually are in physical space. But density altitude? That's the altitude your aircraft engine and your wings think they're flying at. Because airplanes rely on physical air rushing over wings to create lift and packing into engines so they can essentially breathe, the actual physical density of those air molecules matters a ton. And since density changes drastically with temperature, it changes the way the entire plane flies. Here's the golden rule for density altitude. Pressure altitude shifts by 120 feet for every single degree of temperature deviation from the standard. Think about taking off from a runway that is perfectly at sea level, but it's an incredibly hot summer day. Let's say it's 15 degrees hotter than standard. Your plane's performance is going to degrade immensely. The air is so thin and expanded that, to your wings and your engine, that sea level runway literally feels like it's nearly 2,000 feet up in the mountains. A hot day can rob your airplane of so much vital performance that you might need vastly more runway just to get off the ground.
And finally, Section 6, the hidden power of humidity. We're pivoting away from pressure and temperature to look at the invisible engine of the atmosphere.
Let's talk about saturation vapor pressure, or SVP. This is a massive concept in meteorology. As air heats up, its capacity to hold invisible water vapor increases. The SVP depends entirely on the temperature and the evaporating surface. Basically, the warmer the air is, the more invisible water it can pack away before it hits an equilibrium point. Once it's fully saturated, it has to spit that moisture back out, which we see as thick clouds, dense fog, dew, or even dangerous frost in a wing.
And that brings us to something that frankly blows my mind. Water vapor makes up a tiny, almost microscopic fraction of the atmosphere. We are talking just 0 to 4% of its total volume. Yet it is literally the single most important determinant of weather and climate. Why? Because water vapor is essentially a massive battery of latent heat. When water evaporates, it absorbs energy. When it gets lifted into the atmosphere, cools down, and condenses into clouds or rain, boom, it violently releases all that stored heat energy. Despite making up such a tiny fraction of the air, that latent heat release is the literal engine driving atmospheric motion. It's what creates turbulent, convective weather, those towering, bumpy thunderstorms, and just immense atmospheric power.
So what does this all mean for us? Well, the next time you look out of an airplane window at a clear blue sky or a sea of fluffy clouds, try to remember what's really happening out there. Knowing that your altitude can be a calculated illusion, born of pressure and temperature tricks, and that the clear air is packed with a tiny percentage of water, holding just massive latent energy. I really hope you leave this explainer with a profound new respect for the incredible science of meteorology. It's definitely not just weather. It's a dynamic, invisible ocean of physics. Thank you so much for learning with me today. Stay curious and always keep questioning what you see.